Yes, I'm here.
All right, morning.
Good morning to yourself. Good afternoon, I should say.
Yes, indeed. So very good afternoon and very good morning to everyone who is here today for the webinar. So my name is Chien. As you can see on the left, I'm the Regional Head of Marketing for Asia Pac and the Middle East. And we also have Alan Parker here on the line.
Hi there, everybody.
We're just going to give it a couple of minutes for people, because people are still trickling in. So Alan, perhaps you can give us a bit of background information on yourself while we wait for people to trickle in.
Yeah, no problem. I've been working in this industry for 40 years plus. I was responsible to a service provider, global service provider, for about 32 years. I've been involved with guided waves since 1992, early 90s, when I used to work for a large oil company, where they first brought the actual technology onto the site, and I was the engineer given the responsibility of taking them around. So my actual experience with it all goes way back then. I've also then got back in touch with them. That was in Imperial College back in 1998. And I've been involved with the technology for 20 years plus. So that's my background. I've been involved with advanced NDT for about 35 years, right? So I started the advanced NDT with this international company, and obviously been doing it until present. I joined with Guided Ultrasonics in October, and I'm now the Technical Services Authority, and also I carry the Guided Wave Level 3. So that's my background. I hope that's enough for yourselves.
Thank you very much, Alan, for sharing your background with us. Wow, very long history with NDT and with GUL as well. That's great. Yep. So looking forward to meet up more with you in person once the pandemic has loosened. Look forward to catching up with you again in London. I haven't seen you in a couple of years, actually. Although we talk all the time on the phone and over email. Okay, so how are we doing for time? Ready to start? Okay, so again, very good morning, good afternoon, everyone. Thank you for joining us today for the first ever live QSR1 demo session. So right now I'm joined here with me, I have Paul Chen and Mr. Yan Yi Lee, who are my colleagues, and we are broadcasting from the GUL Asia Pacific office here in Kuala Lumpur in Malaysia. All right, and so today's presentation will be interactive. I decided to try something new to keep people awake at 4 p.m. in the afternoon. At least it is 4 p.m. over here. So if you would like to join in and participate in this presentation, feel free to join. I would recommend using your mobile phone to either scan the QR code or just go to this URL, which is ahaslides.com/QSR1. But no worries if everyone is not ready to join in, because I assume it's maybe a bit complicated due to the current setup, but let's just see how it goes. Okay, so I guess most of you know that today's topic is, I will be covering a demo on how to use the QSR1 to size our corrosion. So as you can see behind me, we have a 10-inch carbon steel pipe, 10-inch in diameter. It's about 1 meter long. There are two external damages on the outside of the pipe used to simulate corrosion on the pipe support. There is also an internal defect within the pipe, and that internal defect is actual corrosion, because this is an ex-service pipe. All right. Okay, so let's just start. So just a warm-up question, just to find out a bit of the audience background. Let's see whether we have enough participants on the AHA slide. So the first question, let me see. 1 second, guys. Right, so you should have access to the questions right now. That's great. We have an equipment manufacturer here today. So this is just to get a bit of insight into the background of the audience. Okay, we've got, have we got any service providers here? Looks like we've got one asset owner, possibly a pipeline owner, but this will be more relevant to you. So far, no distributors and others. Okay, I think people are still warming up to this. Anyway, I move on. So my background is chemical engineering and mechanical engineering. So I have a PhD in guided wave from Imperial College. I'm also a level 2 guided wave operator, and I have more than 7 years of experience with guided wave technology. And we are GUL, and we are the leaders in guided wave technology, and we are the experts in this technology that you can trust. And when you use our systems, our equipment, you have the confidence of having an accurate and reliable system, because we are the inventors and pioneers of guided wave technology, and we hold the key patents for guided wave technology. And in addition to that, you'll have the backup and support of 30 years of our 30 years of experience in both research and in the field for guided wave testing. So GUL is a R&D or research and development focused company where we spend most of our resources developing the guided wave technology. But obviously, we are also the equipment manufacturer for the systems, such as the G4 Mini and the QSR1. And we also create and conduct training courses for guided wave testing, and as well as offer consultancy services in the form of data review and field support. So here are our 4 main solutions. Namely, firstly, we have GL screening, which is our very core conventional product, and that includes the equipment for rapid detection of corrosion in pipelines, specifically or originally designed by Dr. David Alain for detection of corrosion under insulation. Okay. And secondly, we have GL monitoring, which are specially designed equipment and sensors for the purpose of detection and monitoring of corrosion or other types of pipe damages. Okay. Thirdly, we have Sub-C, which is a combination of both screening and monitoring, but applied to pipes that are underwater. Okay. And last but not least, the GL scanning is the latest addition to our portfolio, and it focuses on sizing corrosion, especially at pipe supports. All right. And this is this is the focus for today's demo. All right. So again, just a quick background check on where everyone is dialing in from. Okay, we've got one from Asia Pacific, one from Europe. Great. Okay, good. Well done. There's mostly Asia Pac and Europe. I'm pretty sure we have some people from the Middle East, but maybe you guys are not, jumping in onto this quiz. I'm pretty sure I saw some people from Middle East on the list. But anyway, let's move on. So GUL is known globally, and we have over 5,500 systems worldwide, distributed across 250 customers and over 50 countries around the world. All right. So we are a global brand. Okay. Just so because the topic of today is cups or corrosion under pipe support, just a quick show of a survey of what you think cups are. I think most of you probably already know what cups are. Yes, perfect. The answer is indeed B. Well done. Okay. I see a lot of hands being raised. Not sure what's that. But okay, yeah, 7. Well done. Okay. So that's cups. So just a bit of insight onto cups. It's what happens when you have water trapped in the crevice between a curved surface of the pipe and typically the flat surface of a support. And the water trapped in there could lead to damage of your pipe coating, which eventually would lead to corrosion or metal loss in your pipe wall. Okay. So the first thing about inspection is being able to find or detect the location of these defects. And the two most efficient way to find the defect or for detection is firstly visual. So everyone has a pair of eyes. You can do a walk around on your site, and you can visually detect corrosion on the pipe support because it is an external form of damage. Okay. And secondly, we have guided wave screening. Okay, so if you have a very long, if you have 10 to 100 kilometers of pipe, and so we will recommend that guided wave screening is the most efficient way to inspect it. Simply apply your transducer or your sensor at one location, and you're able to inspect tens to hundreds of meters of pipe and accurately determine the location of the corrosion under pipe supports. Okay, so great. Now we've detected where the location of the cups are. What do we do next? Well, the next thing we need to do is sizing. Okay, and why do we need to size? Well, we need to size so that we can perform a form of fitness for service assessment, so that you can understand the condition of your pipe. All right, but the challenge lies in sizing, not detection, sizing. And the problem is that firstly, it's due to the lack of direct physical access to the damaged location. So obviously you can see here the support is getting in the way. So that rules out a lot of NDT methods that only requires direct access to the location, such as UT. All right. And secondly, the corrosion of the pipe support damage is non-uniform. So therefore, the damage profile would change with the pipe circumference or with the axial distance of the pipe. Okay. And thirdly, if you were to choose the right NDT system, you would need a system that is able to account for unpredictable surface properties. So what I mean by that is that every pipe that you encounter, every support location, you will find that the conditions will vary from one to the other, because no locations will be the same in terms of the amount of paint being peeled off, or the thickness of the paint, or how does the support pad affect the location. Okay, these are things that a good system needs to pick up on. So this is where the QSR1 fits in, and why most of you are here. The QSR1 is our latest guided wave scanner that is used to size corrosion under pipe support. And what makes it stand out from the others is that we do it quantitatively, accurately, and reliably. So jumping right into it, this is the heart of the webinar today, which is the demo. All right. Good. Hope you guys can see what we have here on the table. So we've got our QSR1 equipment in parts. So this is what you guys will be purchasing, and this is what you have before you mobilize onto site. So we will show you how the QSR1 is set up. All right. So the first step is the frames. Okay, and the frames are you select the frames based on the inspected pipe diameter. So for example, here today in our office, we have a 10-inch pipe. So we will be using the 10-inch frames. So just a bit of insight onto the QSR1. If you are an owner of the QSR1, so one system is able to inspect a range of pipe sizes from 6-inch in diameter to 24-inch. Okay, so let's begin with the attaching the frames. So simply, you'll be provided with these screws that you put on to secure the frames onto the pod. So we call this the pod. Okay. And the other frame, which is secured on the other side with 2 thumb screws. Okay. Also, guys, if you have any questions, please feel free to use either platforms to leave your questions, and we will address them. Okay, great. So we've attached the 10-inch frames to the QSR1. That's good. Everything is nice and tight now. The second step is to move on to the sensors. All right. So the first thing we'll need to do is to remove the flux keepers. The flux keepers are these metal parts that protect the sensors. These are electromagnetic acoustic transducers. So they operate by having permanent magnets in them, okay? And these are so this is the transmitter, the transducer that is transmitting the guided wave signal, and that will be attached on to the frame like so, okay? Then we take the receiver, which is the blue one, and we slide the card, the transducer card, onto the frame, okay? Next, we would need to secure the card to the frame using another additional 4 screws. And the other 2 on the other side. Nice and simple. So just notice that we're not using any additional tools aside from our hands. Okay, so they're all nice and tight, they're hand tight. Okay, done. So finally, before we place it on the pipe to be inspected, we'll connect our signal cables. Just align them and they should fit in. I think I've had too much coffee, hands are shaking as well. There you go. There you go. Okay. All right, great. So the next thing we'll do is let me just move this out of the way. We will pick this up, okay, and we will place it on the pipe like so. All right. Okay. And what I would do normally is I would just push it slightly to the front and slightly to the back, just to ensure that the QSR1's movement is unhindered. So the thing to know about the QSR1 is it is not a manual scanner. It is a semi-automatic scanner, which is controlled via the laptop. Everything okay? All right. Then, okay, so it is controlled via the laptop. So we would have to connect it to the laptop via a USB cable. USB cable are generally easy to work with in the sense that it connects and cooperates with the computer rather fast. Okay, so I connect one end to the QSR1. I also turn it on. Okay, and I will be connecting the other end to the laptop. All right, and that is the hardware setup complete. All right, hope you guys are still with me. Now I will need to share my screen, my software. So just give me a second. Sharing both screens. Okay, so you guys should be able to see my screen now. Great. Okay, so all you need to do is just open up the WavePro QSR software. Okay, it's done so. I'm going to just move this to the side. There you go. Get this out of the way. All right, give me a second, guys. Okay, present and share, and okay, we're back in business. Okay. Right. So the next step is calibration. So when it comes to the QSR1, the term calibration will vary from any NET equipment to not to any other, vary from equipment to equipment. But for the purpose of QSR1, calibration involves a configuration step that the QSR1 will automatically perform in order to determine the optimum inspection this is all done automatically. All right. All we've got to do is just press the auto configure button over here. And I'll hit OK. There's already some information regarding the system and my location. These are important data that you can include. All right, and now the QSR1 is automatically performing its calibration. So what is happening is that we select the optimum frequency based on the pipe wall thickness, and the frequencies of the system is controlled via the spacing between the magnets, because we are using an EMAG base. All right, so if you look on the bottom left of the screen, you can see that the calibration step took only 49 seconds. And the QSR1 has recommended these two spacings to be the optimum. So that means that there are certain frequencies that correlate to these spacings. Notice that during the setup, I did not input any information regarding the pipe size. The software has automatically detected that it's a schedule 40 pipe, and the nominal wall thickness should be 9.27 millimeters. Okay. The signal to noise ratio is high, it's close to 60 dB. That's great. Also notice that the equipment automatically detects the frame size, so you don't have to worry about that. So no form of manual input is required. And what else to highlight? Yes, on the bottom, on the right here, we can see two numbers showing the top and bottom path thicknesses. So these are the thicknesses that the QSR1 has measured at this point. All right. So that's done for calibration. Nice and simple. Just hit the button and make sure that the status is good. Well, what's next? Well, the next thing is data collection. So we will be performing a scan on this 1 meter long pipe that you can see here in the video feed. I hope you guys can see that the QSR1 is on the pipe. All right. And typically I would be, the inspector would be walking alongside the QSR1, but for the purpose of this demo, I will be behind the QSR or behind the camera to operate it more efficiently. Okay. So data collection, right? So there are a lot of configurations that you can change with respect to the collection parameters or the scanning parameters. So the collection means being able to change the number of averages, for example. Maybe in certain cases you have a noisy pipe, so you might want to use a higher number of signal averages. And in terms of scanning configuration, it's mainly to do with how far you want to inspect and how many steps, how many centimeters per step. So because the scanner is going to move forward, in this case, every 1 centimeter, and it will be scanning at every 1 centimeter. So it depends on the resolution of your inspection that you require. Okay. But for the purpose of this demo, we'll be using the fast scan option. So when you're ready, just hit the button. Okay, so the QSR1 has started scanning. So notice that it is moving semi-automatically. And on the right-hand side, on the software, you will start to see a plot of thickness in millimeters against axial distance, okay? And 0 represents the start location of the QSR1. And and the rest of the distance from there on in the positive direction represents the numbers on the x-axis. Okay. Just to give a bit of insight on the pipe that we're inspecting here today, we are expecting to detect and size 3 different defects. The first one that the QSR1 has detected is an internal defect. So there is internal corrosion within this ex-service pipe. And there are also two further external defects on the bottom of the pipe that represents or simulates corrosion under pipe supports. So as you can see, let's focus back on the plot on the right in the software over here, right? We have the live measurements of the QSR1 as it scans along. So it's currently scanned at about 10 centimeters now. All right. So while it is scanning, we will just press on ahead with our presentation because it will take a few minutes for it to finish. Okay. And just to go into the details about how it works. So the QSR1 is transmitting guided wave signal from the one of the sensors and receiving it on the other end. Okay, so we are using shear guided waves in this method. All right. And how does it work? Well, in comparison to other guided wave systems out there, we are transmitting and receiving circumferential guided waves. And we go beyond the conventional amplitude analysis, which is a very primitive method, and does not account for a lot of effects such as coating liquid inside the pipe or other forms of attenuation. And the advantage of extracting all these frequency contents from this from the raw signals is that we are able to quantitatively and accurately compute or calculate the wall thickness measurements using our proprietary algorithms, okay? And that essentially allows us, again, to be quantitative and accurate, okay? So we don't rely on looking at the change in amplitude between a good and bad signal. We focus on calculating the the remaining wall thickness for each location. And this a good analogy to describe this phenomena or this frequency-based analysis that we are using is to consider a cup filled with water. All right. So if you fill a cup right up to the brim and you start rubbing the edge to generate sound, a resonant sound, you will hear a relatively low pitched sound, which is analogous to a good pipe. So you can think of something like, all right. But when you have a bad pipe, or a pipe that is corroded, it is analogous to a cup of water that is, less than half full, for example. And that, when you create a resonant frequency within this cup, you will notice that the pitch of the noise is higher. So it will sound something like this. So it has the pitch or the frequency has changed, and that is analogous to when there is a defect and when there is no defect within a pipe. Okay, and we're able to accurately calculate, because we're able to calculate the frequency content and quantify them, then we are able to also quantify the remaining wall thickness. All right. So if we go back to our software, to our actual scanning right now, we have successfully detected and sized the first defect. That's great. So we've got the other defect to go. So I shall continue telling you more about the QSR1, right? So again, when you purchase the QSR1 system, it will cater for a large range of pipe sizes from 6-inch to 24-inch. These are the conventional pipe sizes where cups can be found typically. And they all have ID chips in them for you to automatically record these details. So these are not something that you need to manually input into your report, okay? And just to, and the QSR1 is specifically designed for simple resting support. So the application of the QSR1 is for pipes that are resting by gravity on supports. So this does not include clamp supports where the supports hinders the movement of the QSR1, and this does not include welded supports as of this moment. Okay, so we are continuously developing and looking into expanding the applications of our system. All right, and today's demo so far, we have demonstrated a lot of the curriculum or the subjects that it is covered in the level 1 course of the QSR. Okay, and such as assembly of the hardware, some basic guided wave theory, which we didn't really cover, and the data collection procedures such as selecting your collection and scan configurations. These are all covered in level 1. All right, but the level 2 will be the course that will cover this the technique and the frequency analysis method in much more detail. Okay. Also worth noting that these GUL training courses are recognized by British Standard and ASME as well, ASTM, and as well as it complies to ISO standards. Okay. So back to our demo pipe setup for now. We can see the third defect coming in. So we're going to stop the scan soon. All right, so right now we haven't stopped the scan, but right now we have inspected up to, well, we've scanned up to 50+ centimeters, and I think it is roughly about 7 or 8 minutes now. Okay, so we will stop our QSR1 because we have found the 3 defects. Okay, and this is the beauty and the advantage of the QSR1 is that you will get the quantitative and accurate measurements of the minimum remaining wall thicknesses at your pipe, especially at the pipe support locations. Okay, so here we have found the first internal defect. All right, we can just label it here. Internal defect. That's great. And this is the second defect that we found, defect A, and this is the third defect that we found, defect B. Okay, so I am reiterating again what this plot is showing. So this plot is on the top is showing, if we just focus on the black line and the red line, okay, the black line shows the remaining wall thickness on the top half, or the top section of the pipe, and the red shows the remaining wall thickness on the bottom section of the pipe, where we expect the corrosion under pipe support to be. All right. And going back to the idea of the level 2 course and frequency analysis, is that the level 2 course will cover into more details how do we analyze the frequency components of the signals, and how do we improve the accuracy of the system based on the frequency data that is shown. Okay, so a level 2 QSR trained inspector would be competent to analyze all these data to further improve the accuracy of the results. Okay. So finally, we have reporting. Okay. So for reporting, it's nice and straightforward. You have a couple of options, but personally, I find the Excel file being the most useful. So just hit File Export, and we would just go to Export. Okay, there's a bunch of parameters that you can change, but essentially, if you hit Export, then you would get your Excel file out. Okay, so I'll double click on my Excel file, and you will see that the software has automatically tabulated your data in terms of millimeters wall thickness. Okay, and there's a nice little image file for you to use here as well. Okay, and it's as simple as that when it comes to reporting. But if you guys have any further questions, feel free to ask us. Maybe Alan can share more insight into the best way to create reports. Okay, and let me stop my. Give me a second, guys. I'm going to share back the other screen. Monitor 2, great. Okay. Is that good? All right, great. So a lot of the questions that we get from people is how accurate is the QSR1? well, it has been validated by external, by independent studies, including Hoyt, which is one of the leading UK NDT research-based council. And this data over here specifically shows the data of a laser scan compared to the QSR1. So this is an X-service pipe with real corrosion under pipe support, and it's a 12-inch pipe. And in conclusion, the accuracy was found to be plus or minus half a millimeter. Okay, and there's a lot of evidence of the, a lot of our customers have also vouched for the reliability and the accuracy of the QSR1, and you can talk to us more about that. So here's a typical case study that combines the use of both GUL screening and also GUL scanning to carry out a successful corrosion under pipe support inspection. So you would use the GUL screening equipment to firstly find the locations of the good or bad support. So in this case over here, we have inspected close to 60 meters of pipe. And typically these type, collecting data from a GUL screening rings will only typically take about 3 minutes, including placing the ring onto the pipe. And we have shown that based on the 3 support locations here, or 4 support locations here, we have found that 2 of them have a certain degree of corrosion under pipe support. Okay, so we have found that the 2 support locations are needs to be investigated further. So we use the QSR1 to size the corrosion at these supports, and the QSR1 is able to tell you what the what the remaining wall thicknesses is. So in this case, we have found it to be within 70% of remaining wall thickness. Okay, and that is the power of the QSR1. And in the future, we know that the QSR1 has its limitations, like all equipment. Namely, the limitations involve the range of pipe sizes. We keep hearing feedback from our customers saying that they need to be able to inspect larger pipes, or they need to be able to inspect smaller pipes than 6-inch. They're also encountering cups at their clamp supports and also at other places. So therefore, we are happy to announce that we will be launching our AXIAL sensor, which would complement the QSR1. So that means that it will work together with the QSR1 in combination, and it will be able to account for a larger range of pipe sizes. That means beyond 24-inch and below 6-inch pipes, diameter pipes. All right, and it will further expand the application of the QSR1 to clamp supports, and also the sizing of corrosion at interfaces such as the soil air interface or concrete interface. Okay, so that is the end of our demo for today. Thank you guys for those who are still here with us today. So I will be, so Alan, feel free to jump in at this point. We will try to see if anyone has any questions. There is one question at the moment. Well, we have how many questions? About 10 questions, I think.
Okay, can you hear me, Chen?
Yes, I can hear you. Shall I read you the, can you see the first 2 questions on the screen?
Yes, I can read it. Obviously, the first question is, can this technology be deployed on vessels rather than pipelines? I think you covered that particular one with obviously the actual scanner. So obviously a larger diameter can be handled. Obviously depends on the configuration and what you're looking for on the vessel. For instance, supports holding the vessel could be feasible, but also it's going to be combined with, because the QSR at the moment can only do 6 millimeters to 13 millimeters, but they are now increasing the size or the thickness of the material, and this obviously in due course would be up to 26 millimeters. So that makes certain things on vessels a little bit more feasible. Right then, so is that sufficient?
I hope that answers your question, Costa. And the second question by Costa is your technology deployable on steel tubes and detect deposition on the inner tube surface? The tube wall is approximately 3 mil thick.
Well, if you notice at the moment, again, the restrictions on the QSR is for material over 6 millimeters.
So Costa, just to add on to that, is we didn't cover this in the webinar, but the range of applicable pipe thicknesses is from 6 mil to 13 millimeters. So your tube wall is too thin for our QSR1. All right, Alan, so there are a few other, well, there are many questions on the GoToWebinar site. So I will read you the first question. So there's a question that asks, how much is the maximum corrosion detectable on 10 millimeter? So I assume that's a 10 millimeter thick pipe. So he's asking, what is the maximum corrosion detected on a 10 mil thick pipe?
Right, now there is obviously a good answer for this. First of all, on 10 millimeters, right, half thickness, which is 5 millimeters in this case, right, is the first one is quantified, and after the 5 millimeters, which is half wall thickness, it goes into more of a qualitative representation, right, of it. So accurate sizing to 5 millimeters, and then a qualitative sizing from 5 meters to through hole.
I hope
is
that answers
okay?
your question. Yeah, I hope that answers your question, Mario. If you have any further doubts, just send us an email and we'll try to explain it to you better over the phone or over email or over a private conference call. Next question. Give me a second. Okay, so there's a question by Mr. Lee. He asked, what is the maximum wall thickness range inspectable?
Right, and obviously going back to obviously the comment I made just a few minutes ago, at the moment it can do minimum of 6 millimeters to 13 millimeters, but there is in process at the moment and could be out in the next month or two, right? There is going to be an addition to the thickness that could take it up to 26 millimeters. So at the moment, presently as we speak, it's 6 to 13 millimeters, and in a few months' time, there will be additional sensors that you could purchase that will cover up to 26 millimeters. So those sensors would work from 14 millimeters to 26 millimeters.
Thanks, Alan. Again, another question by Mr. Lee. What is the maximum paint or coating thickness allowed on the pipe?
Right, the maximum coating is 1 millimeter. Now then, this particular one it's purely because the EMAT probes, because it's got a default of 0.5 for it to run smoothly on the surface, and then the coating then is the other millimeter, so the maximum from the sensor to the primary pipe is 1.5, so the coatings can't be more than a millimeter. What my experience has been in the last 3.5 years that I've used it, what you can do is smooth the area where the actual sensors go there, and then obviously by, say, removing a little bit of the coating to be below 1 millimeter, you can actually do the scan. The other thing is, right, that the condition of the coating can be in various stages of corrosion. That's all we got to have is where the sensor heads is, but it's smooth for it to move along the inspection area.
Okay. There are two questions regarding the applications on welded pipe supports. One again by Mr. Lee, and so perhaps you can just address that question. I think that answers a few of the questions that we have. So can it be used on welded pipe support?
Well, at the moment, it cannot be used on welded pipe supports, but with the advent of the actual scanner, this obviously application could be restricted, but could obviously give a solution to some welded supports.
Next question, can it be used on elbow or reducer pipe fitting?
No, that was a plain no, purely because obviously of a different configuration that it's running on. As pointed out in the demo, obviously the actual frames run obviously on the pipe and its diameter, and obviously during the inspection of it, but you've got a problem if it reduces, or obviously that it goes around an elbow. For instance, an elbow usually has a thicker one to start with, so you find that the straight pipe and the elbow got different thicknesses, and obviously the actual QSR cannot run on that type of surface. Okay. But again, the answer could be when we bring out the actual scanner, this will obviously give you more options.
Great, okay. Can it be influenced by external noise? Question by Mario.
Right, obviously I take it external noise means vibration going through the pipe and everything. And that's obviously when obviously it can affect it, but this is where the level 2 comes in to see to get the optimum sort of for that type of problem, you can get the optimum inspection on it. So it basically requires a little bit more technicalities to actually look for the optimum frequency to use.
Okay, can it detect pinhole or through wall pinhole defects? Are they detectable?
No, definitely no. Right, it can obviously pick up a profile, that's what it's been done for, and then obviously it can pick up different various type size, but for a pinhole, which is obviously very small diameter and very small volumetric, it's not suitable.
Right, this is an interesting question. What is the minimum length of defect can the QSR1 find?
That's fairly good. It's the actual say is quoted as 30, so I take half of that, that's 15, right? So it's looking at something around between 15 and 20 mil in its profile.
All right.
Bearing in mind that obviously the profile starts very slowly and peaks and then goes, so that's obviously the full dimension of the actual length of it.
Okay. What about defects in pipe with welded saddle plate? Can you detect the defects in
So basically
pipe?
what you're looking at is a welded saddle support. So that's been covered obviously with the answer I did with the welded type support.
Perfect. Okay. Let me find, there's a lot of repeating questions, so I will skip past those. Okay, so is the QSR1 able to pick up internal or external fittings? Question by Mr. Adib.
Okay, obviously go back again, isolated pit, it depends on the dimension of the pit. for the sizing of it, but the QSR can pick up remaining wall. So if you've got corrosion inside, as you demonstrated on the demo, but it will pick up internal and it will pick up external, and it will pick up the difference between internal and external, just giving you the remaining wall.
I think so. I understand it. I hope that answers your question, Adib, with regards to internal and external pits. I think to summarize that, it just depends on the dimension of these pittings. A single pit, no. Cluster of pits, yes, but depends on the axial extent.
That's right, Chair.
There's a question by Mr. Dong. Do you have a QSR1 forum that end users can discuss and share their concern and problems or matters between end user and GUL?
Well, to be quite honest here, we do actually work with the client in obviously coming across. And as you mentioned during the demo, we can audit and look at by obviously using the cloud part of the QSR. So we can actually give confidence to the client that we can audit work done and everything else. And obviously the independent ones, as you mentioned, like organizations like Hoist, do blind trials, and obviously that is open to the clients as well, because most of the information from there is client-led. I hope that answers the question.
So my input on that, Mr. Dang, is that the short answer is no, we do not have a forum at the moment, but I think what Alan is saying, that we can, we work closely with our clients. So if you have any issues, just contact us, and we are typically quite fast with responding, so just contact us directly. But we don't have a forum at the moment. But that's a very good suggestion. Perhaps we will action that. Okay, so this is I'm not sure if I have asked you this question, Alan, but what is the minimum detectable size of the defect? Let's assume wall loss. So what is the smallest wall loss you can find? So let's assume we have.
You have asked the question, Chen. I explained that a few questions ago.
All right. What is the maximum pipe surface temperature inspectable?
That's obviously there. It's about 70 degrees C. Obviously, I'm going to be careful here because Fahrenheit and centigrades are used in different parts of the world.
Yeah, got it. So the next question is the QSR1 able to detect weld preferential corrosion or wall loss on the weld?
No. And the reason for it, obviously, the QSR in its present form, right, cannot negotiate a weld.
Okay. I'm just looking for non-repeating questions.
I understand that.
Because a lot of questions are on the minimum detectable side. Oh, there's one. Oh, there's some on the AHA side as well. Savi, I'm very sorry I joined late. I couldn't see the calibration. I heard that would it be possible to repeat the calibration? So don't worry, Savi. We will be posting this on YouTube, so you can go back and rewatch the calibration step. But typically, it is less than a minute. It was only 50 seconds. But you can watch it on when we post it on YouTube. Does the surface defects? Okay, so here's the next question, Alan.
I can see it. It's caught up. So basically, there's surface defects under the scanning probes. But quite honestly, when you actually even calibrate, right, the actual instrument will pick up saying, but obviously there is something wrong, please find a different location, right? So that is built into the instrument. So if you happen to start calibrating, it gives you a warning saying that you're on top of a defective area. And then obviously what you've got to do then is find a suitable area that has no defects, calibrate with it, and obviously if you can't get anything on there, you can use a historical one with the same thickness and actually put in on the restrictions due to excessive defects, but calibration was done on a similar pipe. But that's how we get over if the actual calibration is happening on or underneath the scanning area.
Okay, I hope that answers your question, Dancho. Again, for anybody, if any of the answers are not clear, feel free to contact us, and we are happy to clarify our answers in more details. Okay, so let's wrap up our session. Thank you everyone for joining here today. Appreciate it. We have finished on, I would say, with 3 minutes to spare. We wanted to keep this session nice and short so that everyone can go on with their work or go home. And thank you very much, Alan, for joining us here today. I know you've had to wake up early for this.
It's okay, because of that new hour in the summertime doesn't mean that I have got to get up too early.
Okay, that's great. All right. So thank you, everyone. If you have any questions, contact us via our website, email, LinkedIn, and goodbye, everyone. Thank you.